Hey guys, Mr. Backberg here. In this video, we're going to look at properties of definite integrals. So the first property we've got is called the zero property. So if we're doing the integral of some function f of x from some value a to some value a, then that integral is going to be 0. Now if we think about this graphically, we're doing an integral, so we're kind of finding the area underneath a curve. So if this line is our curve, and we'll say this is our a value. Well, we're going from a to a, so we're really just looking at this small slice right here. Thinking about that as a rectangle, we've basically got a width of 0. So it doesn't even matter how high up your function is. If your rectangle has a width of 0, then the integral itself, the area underneath that curve, is just going to be 0. The next property we've got is called the additivity property. So if we're doing the integral of some function f of x from a to b, and we're adding the integral of that same exact f of x function from b to c, then really what we can do is one big integral of our f of x function going from a all the way to c. So let's say, for example, we wanted to do the integral of some function f of x, and we wanted to go from 0 to 2, but then we also wanted to look at an integral of that exact same f of x function, but now we wanted to go from 2 to 7. Then really what we could do is the integral of that f of x function, but going all the way from 0 to 7. As long as these b values match up, then you can really just look at one big integral using those end values. So going from 0 all the way to 7. Now sometimes it might be helpful to use this property in reverse. So if you're doing a big integral of some function from 0 to 7, maybe it would be helpful for us to split it up into smaller integrals. Maybe each of those individual integrals are easier to figure out by themselves instead of trying to figure out the big integral. So this property can work in both directions, adding two integrals together to make one big integral, or taking a big integral and splitting it up into some smaller integrals. Now there's also a property dealing with the order of our integration. So notice our integral on the left-hand side here, we're doing the integral of f of x from b to a. Well, if we need to flip the order of that integral, we're allowed to do that, but what we need to remember to do is put a negative in front, or get the opposite of that answer. So typically we like to write our integrals going from our small value up to our big value. But let's say, for example, we were doing an integral of some f of x function, but we were going to look from 5 to 2. Well, here we're going from the big number to the little number. That's not really how we want to have it written. So we can flip-flop the order on those values, but we need to take the opposite of that answer that we're getting. Now the next property is a constant multiple property. So here we're doing an integral from a to b of k times our function f of x. K is just going to be some constant multiple number. And what we're allowed to do is, with that constant multiple, we're allowed to pull that out in front of the integral. And then when we do our integration, we'll just multiply that k value by whatever answer we get. So if we're doing the integral, say, from 0 to 3 of 2 times some f of x function, then what I can do is I can take that 2 and pull it out in front, and then we'll evaluate that integral separately and just multiply whatever answer we get by that 2. Next property is the sum and difference property. So if we're doing an integral of two functions being added or subtracted together, then we're allowed to do those integrals separately and then just add or subtract our answers accordingly. Now the next property is called the max and min inequality property. So if max f and min f are the maximum and minimum values of our function f on our closed interval from a to b, then if we take that minimum value of our function times the difference in our end values, that value will always be less than or equal to the integral value of our function from a to b, and that value will always be less than or equal to our maximum value of our function times the difference in those end values. So it might be helpful to try to visualize what's happening here. So let's say we've got our function f, and we're looking between this a value and this b value. Now I'm going to identify my maximum point on this interval. So my maximum would be right here, and my minimum would be down here. So if we think about what's happening in here, this minimum value, if we were to make a rectangle along this minimum value between our A and our B, compared to if we were to look at the area underneath our curve between A and B, compared to if we were to make this rectangle using our maximum value, the minimum value in here, that rectangle has the lowest area answer. As far as the actual integral, just looking at the area underneath that curve, that's going to be kind of the middle answer. And then if we look at our maximum value and think about making that rectangle, that's going to be the biggest answer that we can get out of looking at these different areas. The last property that we've got is called the domination property. So if we've got two different functions, f and g, and we know that our function f is greater than or equal to our function g on that closed interval from a to b, then the integral of f from a to b also has to be greater than or equal to the integral of g from a to b. Now we can also look at this in terms of our function being greater than or equal to 0 on that interval from a to b. If our function is greater than or equal to 0, then the integral from a to b of our function has to be a positive value, has to be greater than or equal to 0. And that should make sense based on what we've talked about. Functions that are above the x-axis are going to have positive integral answers because they are above the x-axis. So just looking at a few quick examples of using some of these properties, we are given some integral values and we want to use one of them or a combination of a couple of them to help us evaluate a different integral. So we want to figure out the integral of our function f of x from 4 to 1. Well, the part that's going to be important is this middle piece up here. We know that the integral of our function from 1 to 4 is -2, but the order of the integral is written in the opposite direction. This is going from 4 to 1. This integral goes from 1 to 4. But we had a property that said we're allowed to change the order on our integration. We just have to take the opposite of the answer that we're going to get. So it's going to be the opposite of the integral of our f of x function going from 1 to 4. And we know that that value is -2. So this is going to be the opposite of -2, which is just +2. Taking a look at this example, we want to find the integral of our f of x function going from -1 to 4. So the pieces of information that we know that are going to be helpful are this first and this second piece. We can break this integral up into two smaller integrals. This is going from -1 to 4. Well, we know what happens to our integral as we go from -1 to 1 for our function f of x. And we also know what's happening with our integral going from 1 to 4 of our function f of x. So we can break this big integral up into two smaller integrals that we know the answers for. We know that this first integral going from -1 to 1, that has an answer of 5, and we also know that this integral going from 1 to 4 is -2. So if we take that answer of 5 and add that value of -2, then our final answer here is going to be 3. Next example we're looking at here, we're going to take the integral from -1 to 1 of 2 times our function f of x plus 3 times our function h of x. Now there's a couple of things going on in here. The first thing I'm going to do is split up this addition in our integral. So I'm going to split this up into two separate integrals, one of them dealing with 2 times our function f of x, but then we're going to add on the integral of our function 3h of x, so we can separate that addition out using that addition property. But then I also notice that each one of these has a constant multiple on it. So I'm going to pull each of those constant multiples out of our integral and just put them out in front of that integration symbol. So what we're going to be able to do then is use the information that we know about these individual integrals, get those answers, and then just multiply it by that constant value in the front. So this f of x dx going from -1 to 1, we know that that value is 5, but I need to multiply that by the 2 in front. And this integral of h of x going from -1 to 1, we know that that value is 7, but I need to multiply by that constant multiple of 3. Well, 2 times 5 is 10. 3 times 7 is 21. Add those together and we get a final answer of 31. Taking a look at this example, we're trying to find the integral of our function f of x from 0 to 1. Now, as we look at the information that we're given, we know that our integral of f of x from -1 to 1 is 5. But here we're only looking from 0 to 1. Just because the interval length is half the size, that doesn't mean that our answer is going to be half of another answer. On this one, we don't have the appropriate type of information to be able to evaluate this integral. Now, as we look at this one, we're doing the integral of h of x from -2 to 2. Now, we know the integral of h of x from -1 to 1 is 7, but similar to our last one, just because our interval is double the length, that does not mean that our answer is double the size. This one doesn't have the appropriate information given to us. In our last example in this set, we've got the integral of f of x plus h of x going from -1 to 4. Now, based on the information that we've got, we can figure out the integral of f of x going from -1 to 4 by adding up the integral from -1 to 1 and from 1 to 4 for our function f of x. But as far as h of x, we only know what's happening between -1 and +1. We don't know what's happening between 1 and 4. So again, just like we saw in the last couple examples, we don't have the appropriate information for us to be able to evaluate this integral. Now, in this example, we're going to be finding some bounds for an integral. So we want to show that the value of the integral from 0 to 1 of the function square root of 1 plus cosine of x dx is less than 3/2. So we're going to use what we know about the maximum and minimum properties of an integral. And I'm mostly concerned about the maximum value. Now, if we were to look at this function graphically, we would see that the maximum value happens at an x value of 0 on this interval from 0 to 1. And if we were to plug 0 in, the cosine of 0 is 1, and 1 plus 1 is 2. So at the x value of 0, our function has a y value of the square root of 2. Now, as a decimal, the square root of 2 is about 1.41. Now, because of our maximum property, the maximum property says that if we take the maximum value of our function, which is that square root of 2 on this interval, times the difference in the upper limit minus the lower limit, that is the upper boundary of the integral of our function. So we know that our upper boundary is going to be at that square root of 2, or about 1.41. So 3/2 is 1.5 as a decimal, so this upper boundary is less than 1.5. That's going to be it for this video. Thanks for watching.